So, good afternoon, everybody. Welcome to this week's edition of the Heidelberg Joint Astronomical Colloquium. And we're in for a treat because we're going to look into the distant universe at infrared wavelengths, something made possible by the JWST in particular with a lot of input from Max Planck Institute for Astronomy here. So this is really coming, in that sense, close to home. But to tell us all about it is Irene Shivaei, and Irene will be introduced by Leonard Bugert, her host.
Yes, thank you. Yeah, it's really an honor and a pleasure to welcome and introduce Irene Shivaei here in Heidelberg. So Irene obtained her PhD at the University of California, Riverside in 2017, working on near-infrared spectroscopy of galaxies at cosmic noon. She then went to Stewart Observatory in Arizona, where she got the Hubble Fellowship to work on JWST data. There was only one problem, being that JWST was delayed. Fortunately for me and many other people, that gave us the opportunity to collaborate with Irene on other things. And in 2021, you also got the Outstanding Postdoc Award there and continued as faculty. Irene is a member of the MIRI and NERCAM GTO and commissioning teams, and has, as of last year, moved to the CAB in Madrid. So JWST has been launched meanwhile, and we're very much looking forward to what you have to tell today. Thank you. Please give her a warm applause.
Hello, everyone. Thank you, Leonard, for the nice introduction. Thanks, everyone, for coming here, either in person or online. It's a pleasure to be here and share some of our recent results, pre and post JWST, about dust in the universe. So dust exists everywhere, in the protoplanetary disk, around the AGN, in the birth cloud of the stars, in the diffuse ISM, which means that, and now even out to very high redshifts, which means that whether you're interested in physics of ISM or star formation, or you want to design large galaxy surveys to study galaxy evolution throughout cosmic time, or you're a theorist modeling galaxies, you have to take into account the effects of dust because it imprints its effects everywhere, and it's important for precision cosmology and galaxy evolution studies. It is, in terms of mass, it's a tiny constituent of our universe, only 1 to 10 parts per million of the baryonic matter of our universe. But in terms of energetics, it is very significant. If you look at the spectral energy distribution of our universe, of course, cosmic microwave background dominates, but from the extragalactic background, the emission that is coming from the galaxy formation and evolution processes, half of it is from dust, which is called cosmic infrared background. It also has important roles in the physics and chemistry of the ISM, in star formation, planet formation. In terms of cooling and heating of the ISM, it's a catalyst of certain molecules, gas dynamics, and the list can go on and on. And of course, what dust is historically known for, it significantly shapes our view of galaxies by attenuating the light in the UV and optical and re-emitting it at longer infrared wavelengths, which means that it's hiding a significant fraction of star formation in galaxies. These are some beautiful images of nearby galaxies from Spitzer and now JWST on the right, which you can see that there are star-forming regions that are completely enshrouded by dust. And in order to get a full picture of galaxy evolution, you need to take into account this part of star formation. And now in the past decade, with advancements with various advancements in the field, we know that dust also exists out to very high redshifts. We have observed it both in emission and now with JWST, even in absorption with large quantities. So I hope I convinced you that dust is everywhere. And now I want to show you that how it affects anything that you want to actually understand from galaxy processes observationally. As an extragalactic astronomer, however you want to study galaxies around you, you need some of these parameters that I'm listing here to understand galaxy formation and evolution. You may be interested in star formation rate, in stellar masses, ages, or properties of the ISM. To study these, we look at the spectral energy distribution of galaxies. So now in the next few slides, I'm going to walk you through with a simple model of a late type galaxy and how different components of the galaxy shapes the SED of a typical galaxy. So we have stars that mainly dominate the emission in the UV and all the way to the optical and near infrared, young stars dominating the emission in the UV and older stars in the near infrared. We have gas that has its imprints all across the spectrum in emission lines and gas continuum. And then in this picture, we also have dust that mainly attenuates and scatters the UV and optical light from stars and gas, and then re-emits it at longer infrared wavelengths. The shape of the infrared emission depends on both the geometry of dust with respect to the emitting sources, but also the properties of dust grains, their size distribution, their composition. That's what, as a consequence, it's their temperature. That's what shapes the far infrared emission. So to be able to model an SED of a galaxy correctly and to infer the properties that you're interested in, we need to take into account the effect of dust. If you're a theorist, you build galaxies or, for example, build dark matter simulations, you're interested in stellar to halo mass relation, you need stellar mass constraints from observations. If you're an extragalactic astronomer, you want to study the evolution of galaxies, you want to look into the star formation rate of galaxies. And as an example, these two parameters, the stellar mass and star formation rate, can be heavily underestimated if the effect of dust is not taken into account. By a factor of 10 for normal galaxies in star formation rate, and by up to a factor of 3 for stellar mass, you will underestimate it if you don't take into account the effect of dust. So for example, to recover the total star formation rate of a galaxy, as I mentioned, you either need to correct the UV and optical observed light for dust attenuation effects, or you need to directly observe them in infrared for the obscured fraction of the luminosity or star formation rate. Now, putting all of this into the context of cosmic star formation activity, this is the famous plot of star formation rate density as a function of redshift, or the look-back time on the top. We know that our universe reaches a peak in star formation activity around redshift 1 to 3, and then is slowed down. But what I want to emphasize in this picture is that if we actually separate it into dust obscured and unobscured star formation, we see that the majority of star formation rate was dominantly obscured, at least out to redshift 3, 4, where we have direct measurements of dust emission in infrared. And if we look at each epoch, across a large range of stellar masses, star formation rate is dominated by the obscured phase. Here I'm showing star formation rate on the y-axis for the total star formation rate in, let me see if I can find my cursor. There it is. So stars show the total star formation rate, and I guess it's a bit slow. Anyway, stars show the total star formation rate, then we have the obscured and unobscured star formation. And you can see that at these masses, above 10 to 9.6 solar masses, it's dominating by the obscured phase. Now, this is before JWST, which we had to rely on stacks and averages. We can now even see that this in individual galaxies, that a large fraction of galaxies, that all masses are completely dominated by the obscured phase. And I will talk about this plot towards the end of the talk in more detail. But there has been also theoretical advances in the last few years, including or modeling dust in the simulations, either as a component after the simulation is run, or on the fly in the simulation modeling the dust, and in different forms in terms of the general dust or the PAHs, and also around galaxies. But to constrain these models, we need observations. And they are in most part completely unconstrained by observations. So here I'm just showing a few diagnostic plots from the theory side, the dust formation destruction models that talk about how the dust is formed within a galaxy throughout the lifetime of a galaxy, dust attenuation curves, dust to gas mass ratio as a function of gas phase metallicity. And with observations, we are getting there. These are just a few examples at cosmic noon, looking at the variation of attenuation curve, which I will focus on in this talk. and other diagnostic diagrams, both at cosmic noon and at high redshifts. But as you can see, the data points are very scarce and are mostly only at a certain point parameter space of these diagrams. And the challenge, the reason of that is that it's very challenging because we need multi-wavelength observations to understand dust and chemical evolution of galaxies and connect them to the stellar activity in the galaxies. Because as I showed you before, dust has its effect everywhere in the stellar emission, in the absorption, and then in the emission at longer wavelengths. So we need these multi-wavelength observations to put all of this into context. And an important era to study dust and chemical evolution of galaxies is, in fact, redshift 1 to 3, which is called cosmic noon. This is the peak epoch of cosmic star formation activity and black hole activity in the universe. But also, very conveniently, at this redshift, we can probe different phases of galaxy, different components of galaxies, stars, gas, and dust, with reasonable investments of time with our current observatories, from sub-millimeter observatories to our ground-based optical observatories, and Spitzer, and now James Webb, probing the near-infrared and mid-infrared part of it. So that is why a huge part of my research has been focused on cosmic noon to learn as much as we can about as a build-up step to higher redshift galaxies. And in this talk, I will be mostly focusing on the attenuation properties of cosmic noon galaxies and connecting them to the mid-infrared emission, that warm dust component emission. But I will have some transitions to very local redshift 0 galaxies and then also very high redshift galaxies just to make the connections throughout the talk. So I'll start by attenuation. The attenuation curve of a galaxy shows basically the amount of dust attenuation as a function of wavelength, which for simple geometry of a screen of dust in front of the stars, it determines the shape of the observed spectrum. So by knowing the shape of the attenuation curve, we can correct our observations to derive the intrinsic properties of galaxies. But the problem is that there's a large variation in the shape of the curves. These are a few examples of the most commonly used attenuation or extinction curves from Milky Way, SMC, and then an attenuation curve of local starburst galaxies. And you can see that there's a large variation in the UV slope of the curve, which is actually very important because most of the high redshift observations are done in the UV. So correcting it is very important. But because of this variation, it has a huge uncertainty associated to it. And the origin of these differences come from two things mainly. One is the geometry, the distribution of dust with respect to stars. If you have a shell of dust surrounding the stars, or if you have a uniform distribution of dust and stars, or clumpy dust-to-star geometry, the shape of the attenuation curve changes for the same grain composition and size. But also, the grain composition and size distribution matters in determining the shape of the intrinsic attenuation or extinction curve of a galaxy. Smaller grains tend to produce a much steeper attenuation curve. For example, the UV bump feature, which I showed in the previous plot, is coming from carbonaceous grains, while if you have a silicate dust-dominated galaxy, you won't see this feature. And of course, these two effects are completely connected to each other. When you observe a galaxy, it's both of them that is shaping its attenuation curve. But as much as it's a very difficult problem to solve because of this entanglement, it's also a very exciting one because it means that if you find a way to control for geometry, you can actually learn about physics of dust by deriving the attenuation curve of galaxies. And this was one of the motivations of our work. So here, just to show you again, I'm showing some of the most used attenuation curves by extragalactic astronomers. In the background in gray, you have two extinction curves from Milky Way and SMC. And then from redshift 0 to an average curve at redshift 1 to 3, you see that there seems to be an evolution happening, both in terms of the slope, and the bump is starting to appear. In a study a few years ago, what we did, we used the sample of galaxies that were controlled for their distribution of dust optical depth. So that was a way of controlling the geometry effect. And the only difference between the two samples were the metallicity, the gas phase metallicity of these galaxies. And indeed, we saw that if we derive the attenuation curve for low metallicity and high metallicity, which by high I mean like around solar metallicity galaxies, there is a huge difference. The low metallicity galaxies are much steeper, like the SMC curve, and we don't see any distinctive sign of the UV attenuation bump in them, which is telling us something about the evolution, the grain size properties of these galaxies. The low metallicity environment must be more suitable for having a larger fraction of small grains and a steeper attenuation curve. And one of the important implications of this is in the locus of galaxies in the empirical IRX beta diagram. The IRX beta diagram which is on the y-axis, shows the IR to UV luminosity, so basically the amount of obscuration, attenuation by dust. And on the x-axis is the UV continuum, stellar continuum slope. This was originally developed to help high redshift astronomers that by only using the UV information, which they often is the only thing they have access to, correct their UV properties, their observed UV emission for dust attenuation. So basically, if we calibrate the UV continuum slope based on IR to UV luminosity ratio, we can correct the UV for attenuation without having any infrared data. So in this diagram, if you have more attenuation, both axes increase with more attenuation in the galaxy. But the shape of your attenuation curve determines basically the location of your galaxies in this diagram, which makes it again very complicated. If you know that galaxy attenuation curve of galaxies vary from one to the other, and you don't know what is the reason behind it, you would have basically just a scatter plot. So we saw that in a different sample, with a completely different sample and an independent study, we again saw that at a given UV continuum slope, galaxies move up in this diagram based on their metallicity, such that the lowest metallicity galaxies have a very steep SMC-like curve, and the high metallicity galaxies lie on the locus of the Calzetti or the original MIRI 1999 part of the diagram. And this has been also seen in other studies that looked at the location of galaxies in this diagram as a function of stellar mass, such that lower mass galaxies tend to lie on the SMC, and the higher mass galaxies be more shallower curves like the Calzetti curve, which is most likely from the mass metallicity relation, that you have the low metallicity galaxies that tend to have lower masses with a steeper attenuation curve. Now with JWST, we can study similar things, but for the first time at much higher redshifts, all the way into the epoch of reionization. And one of the reasons that now it's feasible is that with JWST, we can get large samples, statistically large samples of spectroscopically confirmed galaxies with redshifts that have are spectroscopically confirmed. So just to give you an idea, before JWST, less than 1% of the known sources at redshift greater than 6 were spectroscopically confirmed. So we are entering a completely new era, having hundreds of galaxies above redshift of 5. This is just an example of showing a GRISM survey, Fresco, in cycle 1, that used NIRCam GRISM to do a survey in Good South. And basically what these sort of surveys do is that they give us flux limited samples going all the way to very high redshifts, depending on where the emission line is moved. And some preliminary results, one of the things we're trying to do is to use flexible SED modeling techniques to fit these galaxies for their shape of the attenuation curve and see that how it evolves to high redshifts. And this is completely preliminary results. We are seeing that the average, so each gray curve here is the attenuation curve of an individual high redshift galaxy, and the orange shows the average. And we see that it's shallower than the SMC curve, which is a bit different than what we expected. We thought that the lower metallicity galaxies at high redshift should have a steeper curve, but that's not what we are seeing here, which is probably because it's preliminary. I'm not going to give you the exact answer at the end, but like it's telling us something about the properties of grains, dust grains that are completely different at high redshifts compared to what we thought they should be. So another part of the attenuation curve that I want to attract your attention to is the UV attenuation bump. The UV 2175 angstrom bump is a mysterious feature in the attenuation curve of galaxies. It centers at 2175 angstrom. It's very broad. It's an absorption feature. It was originally seen in the Milky Way curve that you can see in the background in the dotted gray curve, and very significantly, but completely absent in, for example, the SMC curve, most of the sight lines of the SMC. Also, it wasn't observed in the redshift 0 starburst curves, but at high redshift, there has been different studies. In this work, we saw that it's very significant in high metallicity galaxies and not at all present in the low metallicity curve of galaxies. So why do we see the bump in some and not the others? What is the origin of the bump? And what is its significance? How much it affects our observations? To answer to these questions, we went one step back. The PAH molecules, polycyclic aromatic hydrocarbons, are the suggested origins of the UV bump. PAHs are these carbon-based molecules with edges of hydrogen that they absorb single UV photons and get transiently heated to high temperatures and emit in mid-infrared at certain bands, the strongest of which is at 7.7 micron, which, again, very conveniently for a redshift 2 galaxy, we could observe it with a Spitzer MIPS 24 micron. And at the same time, with our optical telescopes, sensitive optical telescopes like VLT, we can observe the UV bump and constrain it. So this led to a study of redshift 2 galaxies, a systematic study to see whether we can connect directly the strength of the UV bump to the emission of PAHs in mid-infrared. So for that, because of the sensitivity limitations of Spitzer, and that we had to stack MIPS images, our sample is about 100 galaxies, but we binned them in 4 stellar mass bins that I'm showing here in 4 different colors. Then we stacked the UV, rest frame UV spectra and from a VLT, and you can see that the spectra is beautiful. A lot of UV features, the emission or absorption features, I'm showing them with vertical lines, but we were mostly focusing on the region that has the 2175 angstrom bump. We fit a Drude profile, which is the common shape of this feature, in these 4 mass bins. And as expected, we saw that as we go to higher masses, indeed, the amplitude of the bump increases significantly. So these colors correspond to the same stellar mass bins that I showed at the beginning. And at the same time, we see also an increase in the PAH strength from the MIPS 24 micron data. So this is rest frame 8 micron PAH emission. And this is the main plot of the work, showing that the PAH strength on the y-axis and UV bump on the x-axis for the 4 bins of stellar mass are very well correlated with each other, a direct indication that these 2 must be connected. So the symbols show the stellar mass bins, and I'm showing also the few galaxies that we had individual detections in 24 micron for, with the smaller symbols in the background. Now, a quick look at redshift 0. With JWST, we can now do the same analysis on very resolved star-forming regions in local galaxies. This is a work led by Andrew Battisti, looking at the beautiful mid-infrared images, MIRI images of FANG's JWST survey, and connected to observations from in the UV from SWIFT to derive the strength of the bump and the strength of the PAH emission. And we see positive correlation between the two. On the right, you see the diagram of this is a combination resolved star forming regions of 15 galaxies in this sample. So this is redshift 0. And now with JWST, another thing we can do is to look at the bump for the first time at very high redshifts. This was the first spectroscopic discovery of the UV bump in a redshift 7 galaxy. It was very exciting. Of course, we thought maybe the bump exists in very high redshift galaxies. That's why we looked at the spectra. This is near spectra, and the inset shows the magnified part of the diagram. But still, when we saw the bump with this strength, we were very surprised, because this is a very young system. And if we go back to our assumption that UV bump comes from PAHs, PAHs are often thought the main, most common channel of producing PAHs are in AGB stars that require a few 100 million years. So we are talking about time scales of about like a few 100 million years. And this galaxy is very young. So to have this much PAH to produce this bump is a challenge for dust formation models in galaxies. So maybe this is telling us that we need more rapid production ways for PAHs, maybe in variants of supernovae or Wolf-Rayet stars. And yeah, so you can also compare the redshift 7 galaxy in this paper is all the way on the right. You can see that in terms of strength, it's even stronger than the most massive galaxies that we detect a bump in at redshift 2 from the work that I showed you earlier. Now, back to the redshift cosmic noon and redshift 2 universe. All the results I showed you was from Spitzer, which was fantastic. Both Spitzer and Herschel opened a new window to us to understand the infrared universe. But Spitzer was a 85 centimeter telescope. And even though it was cold and sensitive, it was limited by confusion noise. Here, I'm showing in gray the range of infrared SED of typical galaxies at redshift about 2. And with a blue arrow, I'm showing the confusion limit of Spitzer MIPS. And you can see that we were only able to detect individually only galaxies that were basically the tip of the iceberg. We were missing most of the population of redshift 2 and relying on stacking and averaging to get some detection out of them. And now this picture has completely changed with MIRI on James Webb. Not only we have a more continuous wavelength coverage from 5 to 25 micron, but because of its much higher sensitivity, in very modest integration times of 10 to 20 minutes, we can get an order of magnitude better in sensitivity and able to detect the majority of galaxies in this epoch. So this brings me to the survey that I've been spending most of my last few years on, SMILES, Systematic Mid-Infrared Instrument Legacy Extragalactic Survey. It's the US MIRI GTO program, about 70-hour program that observes the good south field in 15 pointing, so total of 30 arc-minute square. And in the first 2 cycles of James Webb, this is the largest MIRI survey that has a continuous coverage of 5 to 25 micron. The integration, the 3 sigma integration sensitivities that I showed you in the previous plot are from this survey. The observations, so this is most of the team, the team, if you know any of the names, are in Arizona, which was where I was based until a few months ago. We got the data in the last part of the data was in last January, but it took us months to finally be happy in terms of doing science with the data in terms of data reductions. And this has been a story not just because of this data. I've been involved in the MIRI commissioning as part of the instrument team before the telescope launch, we were doing testing on the ground, but also after the launch, we were in commissioning. And I can say probably it was the most exciting time of my career as an astronomer. Just being in that environment and getting the first data. So top plot shows the mission control room that we were monitoring in 8-hour shifts, day and night. And a lot of work because we had an actual hard deadline to announce the instrument ready for science. But it was a very exciting time and a very friendly and motivative group of people to work with them. And there were a lot of challenges, as any one of you who have worked with JWST data as a new telescope, it's a new telescope, and there are a lot of challenges from for MIRI, from PSF, flux calibrations, background, understanding the flat filling and background and the reductions. It's been all fun. But we now have, as of a few months ago, our survey reduced. There are more galaxies if you look at actually the FITS files. But what I like about this, this is the footprint of the SMILE survey. What I really like about it is it's like a jelly bean survey. There are all sorts of colors coming in and out in these filters of MIRI. But I want to zoom in on a few galaxies to just show you the capability of MIRI and the SMILE survey in general. So this is a redshift 0.4 galaxy. On the left, I'm showing the NIRCam color image, which of course had a much higher resolution. But we're not comparing with that. We're comparing with what I'm showing on the right, which was all we had in mid-infrared, MIPS 24 micron. The PSF was 6 arcsecond. So the whole of that galaxy is one big blob. But now I'm going to move through different filters of MIRI that are going up and down the PAH features in the mid-infrared for this galaxy. And you can see that individual star-forming regions are coming in and out, and we're actually detecting them for the first time. And slightly at higher redshift, similar story. All we had from this association of galaxies between redshift 1 to 2 was that one big blob of Spitzer. And we did a lot of science, great science with that, but it was very difficult to, and at some point impractical, to individually separate the light of these galaxies and detect the fainter ones. But now with MIRI, as these galaxies, the PAH features come in and out of the filters, you can see that we can individually detect them and measure their mid-infrared emission. So to give you an example in terms of the SED, this is what we have. This is an example of a redshift 1 galaxy. From HSD, NIRCam, all the way to MIRI, we are sampling the SED very well, meaning that we can model its stellar population with a very with great accuracy. So this is a star-forming galaxy. Because of this well coverage in the mid-infrared, we can also now separate the emission from PAHs that are coming from star-forming regions from the much hotter dust that is coming from around the AGN. So the bottom, the SED on the bottom is showing an AGN-dominated galaxy. Because you have a lot of hot dust, you get a continuum in the mid-infrared, which basically suppresses all the PAH emission if they exist from the star-forming part of the galaxy. And then you have the star-forming galaxy on the top, but there is all this range in between of mixtures of star-forming and AGN galaxies that now we can pick out because of this wavelength, continuous wavelength coverage in the mid-infrared. And one of the first works out of this survey was statistics of AGN in Good South. This was led by a postdoc in our team, John Ray Liu at University of Arizona. And one of the main findings was that a large fraction of MIRI selected AGN were never detected before, either in X-ray, radio, or IRAC, which was also mid-infrared, but much lower sensitivity. Even in massive galaxies, about 35% of the MIRI detected AGN were new compared to the previous studies. Well, that's all I'm going to tell you about AGN. If you're interested, check the paper. I am mostly excluding AGN and look at the star-forming galaxies. So this is our sample, about 460 galaxies. I'm showing the star formation rate versus mass parameter space of our galaxies. And the main sequence is shown with a shaded region. You can see that most of these galaxies, these are all MIRI detected. Most of them are in the main sequence with some spread above and below. And we have very good coverage, photometric coverage for all of them. For examples, for a starburst galaxy above the main sequence, one very low mass galaxy, one main sequence galaxy, and one below the main sequence, we can detect the mid-infrared pH emission very well. And one of the parameters that we can constrain is the mass fraction of PAHs. Now at redshift 0, this has been studied extensively in the past with Spitzer mainly data. For example, one of the diagrams that have been studied and discussed a lot is how the mass fraction of dust in PAHs correlates with the metallicity, gas phase metallicity of galaxies. And there are many studies. This is one of the mostly cited ones that I'm showing here. The general consensus was that above a certain metallicity, the pH fraction is almost constant and high, and below a certain metallicity, it suddenly drops to very low values. Now, this has not been studied in this shape at any redshift above 0. So I compiled two samples of redshift 0 galaxies. So this is the similar picture that you saw in the previous one, but with two different compilations because it goes to much lower metallicities at redshift of 0. And there are two samples because there are uncertainties in metallicity determination of this. So just for completion, I'm showing both of the metallicities. That's why they're in two different colors. And here, now I'm showing a moving median trend and a fit to this moving median. So the moving median is on the right, on the top, and the fit to this trend on the bottom for redshift 0 galaxies. And this is our redshift 1 to 3 galaxies. They have a very similar behavior to the redshift 0 galaxies, which is showing us that we are looking at a almost universal pH metallicity relation. At high metallicities, above half solar, we have an almost constant pH mass fraction of about 3.5%, which is very reassuring because pHs are indeed commonly used as a star formation rate indicators in metal-rich massive galaxies. Then at low metallicities, it drops to very low values. It's not 0. Maybe it's a sampling issue, but it's not 0, but to very low values. And in between, we have a very steep linear reduction of the pH fraction when we go to low metallicities. The reason behind this is not completely known, but there are multiple scenarios. It can be that these pHs are not sufficiently produced because of a delayed injection of them into the ISM from AGB stars. Or there are models that are saying that maybe that PAHs are more efficiently produced at high metallicities because of more efficient shattering of larger grains. Or it can be that at low metallicity environment, PAHs are destroyed because of less shielded low metallicity environment, harder ionizing radiation, and more intense ionizing radiation, destroying these small molecules. But it's showing us that this is a universal relation and opportunity, an opportunity to use the ISM metallicity to better understand the physics, dust physics of galaxies at different epochs. Now, I told you about the constant pH fraction at higher metallicity and how that's a good and commonly used star formation rate indicator. So that brings me to the next result of this work, that we wanted to look at the star formation obscured fraction of these galaxies. As I've mentioned at the beginning of the talk, one of the most significant uncertainties in deriving star formation rate of galaxies is how much of it is obscured by dust. Because a lot of times you only have the unobscured star formation and you don't know how to correct it to derive the total star formation rate of a galaxy. Now, before JWST, there has been studies to look at how the obscured fraction changes with galaxy parameters, and one of them is the stellar mass. This is a work based on MIPS data. That's why they're all averages based on stacks of MIPS on Spitzer. And one of the main conclusions was that between redshift 0.5 to 2.5, the amount of the relation between the obscured star formation fraction and stellar mass does not change. It seems like at a given mass, you always have a certain amount of obscured fraction. And as you can see, it's pretty high at most normal masses. But this was based on stacks of galaxies. Now we can look at individual obscured fraction of individual galaxies at a given mass. So overall, we see the same very strong correlation between the amount of obscured fraction and stellar mass of a galaxy. And here the obscured fraction is in terms of UV luminosity, so obscured UV luminosity fraction. But some of the, and compared to the study before, the dotted line is the MIPS-based study. Overall, within the scatter, we agree, but there are some systematic differences. And we think that at lower masses or intermediate masses, the reason we get on average lower obscured fractions is that we are not, the confusion limit of MIPS could have overestimated the amount of obscuration for these average masses, because this is where you get to a point that you cannot separate the light of different small lower mass galaxies from each other. And then at high masses, Spitzer surveys are much, much wider than the MIRI surveys. Even with a 15 pointing and 70-hour survey, we were only 30 arcminutes square. So most likely we are incomplete, very incomplete in the high mass and missing the more rare, very obscured galaxies in there. That's why we are underestimating probably the high obscuration, the high mass and in terms of obscured fraction of galaxies. But there are a few interesting things in this. If you look at galaxies that are dominantly obscured, more than half of their UV light is obscured. On average, galaxies above 10 to 9.5, they're more than half of their emission is completely obscured by dust. But even at lower masses, all the way to 10 to 8.5 solar masses, there are galaxies, there exist galaxies that are dominantly obscured. So what is happening? Why do we have this such a large scatter in this relation from at a given mass, from very low to very high obscured fractions? It seems that it correlates very well with the size or concentration of star formation in the galaxies. So I want to remind you again that this is the first time that we can actually also measure dust sizes of redshift 1, redshift 2 galaxies. On the right, again, I'm showing that comparison with the Spitzer 24 micron. The PSF size, which I'm showing the full width half max of the PSF with a white circle, was 6 arcsecond. Compared to the MIRI 15 micron PSF, which is half an arcsecond. So in all wavelengths of MIRI, we are dealing with a sub-arcsecond resolution, which is a huge improvement compared to before. So when we look at our galaxies, we saw that at a given mass, the spread in the obscured fraction correlates with the size or with the concentration, such that at each mass, here I'm showing a bin, and the sample is much smaller here because we cannot, not all galaxies at these redshifts are spatially resolved. So we have to limit it to those that are larger than the half arcsecond PSF of the 15 micron filter. But on the left, I'm showing the obscured fraction as a function of star formation dust surface density. And on the right, just as a comparison, I'm showing the same dust size, but just the size, not the star formation surface density. And in three bins of stellar mass, we see that there is a very obvious correlation that at a given mass, we have higher obscuration for galaxies that have higher star formation surface densities. So the normalization is generally evolving, which is expected. When you have more massive galaxies on average, you have higher obscured fraction. but at a given mass, it correlates with the star formation surface density. And this can be explained with this very simple cartoon. If you have a large galaxy that star formation and dust is distributed in it, you tend to have a more complex geometry of dust with respect to stars. Some of your stars are embedded in their so-called birth cloud, very thick dust clouds and very obscured. Some of them are more in the diffuse ISM, less obscured. So what you get is a combination of relatively unobscured and completely obscured emission. But if you concentrate all of this in the center of the galaxy, you have a more homogeneous dust around your stars, and you increase the dust covering fraction, so you get a higher obscured fraction. And now these population of galaxies are also very interesting because they can be that starburst episode in that starburst episode on their way to the quenching. Again, this is very exciting to be able to measure their mid-infrared emission, their obscured star formation and sizes to understand their evolution. There's a lot with MIRI to be done, but I want to also keep an eye on the next generation of infrared telescopes. So PRIMA was a mission concept, a probe concept that was submitted in a NASA call for X-ray and far infrared probes. If we get a far infrared probe like PRIMA, which would be in the next decade or so, maybe more, we will be able to do all this analysis, detecting PAHs and mid-infrared dust, all the way to much higher redshift of 4 and 5 with far infrared loops. And this is a gap that we currently have. So it will be a very exciting time to extend all of this while we are still enjoying the amazing new things of MIRI on James Webb. And with that, I will leave you in my summary slide.
Thank you very much, Irene. It's certainly exciting new results, a lot of thinking and analysis underway. We can see that already from what you've told us. Please, some questions from the floor, then I'll ask from the virtual audience. Please, Dulamon's the first.
Yeah, thanks for a nice talk. I was wondering, I mean, I really like this correlation between the UV extinction bump and the PA features in emission, which is very exciting. I was wondering if you see this correlation, but do you also see that these features do not correlate with other things, so that you really know that they are actually related and not just because they both depend on another parameter?
Yes, so in that Redshift 2 study, the main result that I showed, we did control for one or the other. So the main things are star formation rate, for example. You would think that it's like just bigger, getting bigger. So we controlled for star formation and still saw the correlation that it's increasing with mass. But mass, how would you correlate with mass with like grain properties? It's probably the mass metallicity relation. And in that work, we didn't have the optical strong lines to directly measure the metallicity, but we had a lot of, as you saw in the UV spectrum, we had a lot of UV lines. So we estimated the metallicity of galaxies from the UV lines, and they correlate very well with metallicity, which is also probably why we see it with mass. But yeah, we controlled for star formation, which is the main one. I also should add that there are other parameters like age of these galaxies. If you have but then both of them tend to be very low. So in a very young galaxy, you don't see PHs, but also you don't see the bump. They go hand in hand.
Okay. Another question here.
Hi, Irene. Thank you for the beautiful talk. So amazing results. I was wondering if you can comment more on the pH fraction metallicity relationship. Does that shed any light on the production and destruction mechanisms of PAH molecules? Can you comment on that?
Yeah, so we just looking at the pH fraction and metallicity, it's hard to say what is causing it. It can be that they're not produced at low metallicities or that they're destroyed at low metallicities. And so now this is the time that we need theories and modeling, on-the-fly modeling of the dust within the simulation to maybe better understand what's happening. But there are, not at Redshift 2, but in the local universe, there are studies that look at the pH fraction with ionization fraction as coming from ratio of lines. So in the Spitzer time, it was nitrogen line in the medium infrared, or sulfur lines now, like sulfur 3 to 2, that is a very good proxy for ionization parameter. And they see that there is a strong correlation, higher ionization parameter with low pH fraction, which tends to tell you that they're probably destroyed. It's a destruction mechanism rather than not production. But at the same time, there were studies that looked at the age of the galaxy so the Redshift 2 study also look at the age, but also Redshift 0, age of the galaxy. And then you see that in very young galaxies, you don't see pHs as strong. So then it's the production scenario that maybe they're not produced.
Okay. Then let me just have a look. I don't see anything online right now. Oh, wait a minute. I said that, and 2 seconds later, we have something coming through. Yes, so I have a question here from Ania Roots, Ravi Shankar, to everybody, which I'll read out, and then you can answer. Is the effect of variations in FOBS, SF, more due to stardust geometry or galaxy viewing angle? Simulations seem to suggest it could be more due to the former, that means dust geometry, but can we comment from observations?
No, that's a good point. It's something that we are looking at to see if we can see a preferential orientation for galaxies that we have higher obscuration. Although since we see the same trend of higher star formation surface density for more obscured galaxies at all masses, it's hard to think that all of them are preferentially have a different viewing angle. But yes, it can be another parameter that is playing a role in the scatter we see.
Okay, then come back to us, Annie Roots, if you have any more comments on that. Could I just make a quick comment on that? Just a question really about the data. I mean, how well can you identify disk galaxies in your survey, and how well can you sort of calculate the orientation of the disk, and whether that, and have you checked whether that actually does have an effect?
I don't have an answer for the second one. We haven't checked that yet. It's because the morphological analysis has just been started. But I think I have one backup slide that this might answer your. So this is just an example of one of the galaxies. The data is on the left column, and the model in the middle and residual on the right. The 2 rows, the top row has a point source model corresponding to that filter, and the bottom one is fitting it with a CSIC profile. And you can see that very obviously a lot of these so this is just an example, but a lot of our galaxies have a disk, and the point source fit does not give us good.
I mean, just to come back on that again, I mean, you mentioned that you were able to measure the sizes in the dust emission of these disks for the first time. How well does that correlate with the sizes seen in the rest frame optical at various optical wavelengths? Is there a sort of correlation? Because you do see those correlations obviously in local universe galaxies.
Yes. So this is another thing that there's a lot to be done, but one of the studies that it's almost complete from one of our postdocs is similar thing, that's measuring dust sizes and compare with the stellar sizes. And we are seeing that in the LIRG regime, so not very luminous ULIRGs in these regimes, the dust emission tends to be more extended
Yeah.
than the stellar emission, which is not what was found with ALMA at much higher star formation stellar mass regime.
Right, but there's some population of inverted commas normal galaxies which are not powered by powerful central sources. I mean, do you basically see larger optical sources are larger dust emission sources in those things?
That's yeah, I mean, as I said, I think the average trend that we see so far based on the so far analysis is that the dust emission is larger, is
Yeah.
more extended
Yeah.
than the stellar emission. But as I said,
Fascinating.
this is all new and preliminary, so there's a
Fascinating.
lot to be done.
Well, maybe that's telling us something about how these galaxies get their gas or something interesting like that. Who knows? Okay, more questions from the floor. I don't see anything. Any more comments from the online audience? I don't see that. One more question.
I wonder, I guess people have been making spectral analysis of PAHs in the lab, also in the UV, and so why can't it be really figured out in the lab whether this is from PAHs? This feature, this UV.
No, actually, that is why we think PHs are from the UV bump is from PHs. So it's from part of it is from lab work. That that shows that it can be from that. But it's so from like lab work, I'm not that familiar, but a little that I know, it's not a very simple modeling. So you get a lot of profiles in the absorption that tend to make it very broad. But then exactly where it's centered depends on how you're making, what's the composition of those and how they're excited.
Right. Okay, Leinert.
Yes, thanks very much for the nice talk, Irene. I wanted to follow up on the plot also mentioned by Eva on the PAH destruction and formation, whether it's PAH destruction or the lack of PAH formation at very low metallicities that's driving the lack of emission. And I was actually curious if you, I don't know if you know this, but if you have a feel for how would we disentangle between the two? Do we need really theory predictions? Do we don't know enough about the formation scenarios, for example, low metallicity environments? Or is it really that we're lacking? Is there an observation we could make that you could think of that we can do to disentangle between the two? I was just curious what your thoughts are on this.
Well, in terms of integrated light of galaxies, I think it would be informative if we, at the same time that we are measuring metallicity, we also look at just ionization parameter indicators. And then see which one is strong. We can do control for one and look at the other because they do correlate, but not without a scatter. But on the other hand, I think this is where the Redshift Zero studies like FANG's survey can help a lot, looking at a much more result sense, and then see if you can get a better answer in that. And there are FANGs in the FANGs team. There are people who are working on this. Yeah.
Okay. I cannot resist asking one final question since I don't see any more in the audience. I mean, you mentioned this fascinating fact that you were picking up AGNs much more commonly than in previous surveys. Can you give us some hint or some number about what fraction of your galaxies you are actually classifying as AGNs?
Yeah, so if let me go back. Yes, so in this work, this is on the footprint of the survey in Good South. So we found about 217 AGN, which was about 7% of the full population of galaxies that were MIRI detected. 7% of MIRI detected galaxies. Yeah, but out of those 217 MIRI detected AGN, identified as AGN, 80% of them were the new MIRI only detected AGN. Only 20% had overlap with other surveys.
Well, look, thank you very much. I think we'll round off the questions there because I don't see any more in the hall. If I could ask you to put a file up on your screen, which is on that, I think you can plug it in here. And this is just to advertise next week's colloquium. Thank you very much. And then some announcements about dinner tonight. So thank you very much, Irene.